Good afternoon, ladies and gentlemen. I'm Aniket from EDS Technologies, and I will be your host for today's webinar. First of all, we thanks each and everyone for taking out time and joining the webinar, Accelerate Structural Simulation, Automate Pre-Processing Task, and Rule-Based Meshing in SIMULIA. So now I would like to introduce to our speaker for today's webinar, Mr. Kedar Gokhale. So Kedar is a senior application engineer with over 8 years of experience specialized in non-linear structural dynamics, high velocity impact analysis, and crash simulations. He has successfully managed 3D experience Simulia, Abacus, eyesight projects and services across various industries, vertical, and handled multiple customer issues and escalations. So over to you, Kedar.
Thank you, Aniket, for the introduction. Good afternoon, everyone. Thank you for joining us today. So before we start to the technical presentation, I would like to give a brief introduction about our company EDS Technologies. EDS Technologies Private Limited was incorporated in 1994 to focus on providing PLM solutions, implementation and support. We are the largest technology solution provider in India and platinum partner to the Dassault system. We have served more than 2,000 customers and operated in 11 locations across the India in our with our headquarters based out of Bangalore. We have strategic partnership with world leader like US and Optomic for the additive manufacturing, human solutions for the ergonomic solutions for the automotive and aerospace industries, Technia for ensuring product data quality. For military simulation and training needs of the aerospace and defense industry, we have the partner with the MAC, Echelon and Agenium for the visual simulation solutions. We also have a strategic partnership with the ISRI for GIS requirement. With respect to the EDA solution, we closely work with the Synopsys. We have dedicated sales, support, marketing, and customer satisfaction team to address the customer PLM business and support requirements. Now we are moving towards the technical presentation. So this is our agenda for the today's session. So we will be start with the automated mesh generation and rule-based techniques. So automated mesh generation can be governed by the rule. So we can generate a different rule by defining a different parameters. So parameters can be a mesh specification, topology specification, or you can specify the quality criteria and rules for the geometry features such as the hole, fillet, or the beads. And this rule can be you can use for the rules to generate octahedral triangle mesh, tetrahedron mesh, surface quad mesh, sweep mesh, beam mesh, or the partition hex mesh. Then you need to specify the element types. So that can be covered into the meshing rule. So you need to specify the element order, then the mesh size, then the meshing techniques can be there, then the absolute type. So various parameters for the meshing rule. Then you can set up the quality criteria, just like angle tria, angle quad, wrap angle, Jacobian. We can set into the quality. Then for the geometry consideration, we can consider a geometry between the faces, or you can specify the angle between the faces, angle between the curves, or the simplifying the geometry below some dimensions, or the curvature angles. Then you can capture or the neglect the particular features below the particular dimension or above the particular dimension. So now we are going to see the demonstration for this rule-based technique, how to create a rule, how to apply to the particular assembly, and how we get the correct mesh and optimize mesh when we use this rule-based automated mesh technique. So here you can see this is the specific cradle assembly from the automotive domain. So here you can see the different parts of the cradle assembly, and you can see the blue lines over here which are representing the welding location. So spot weld locations are also there. It is specified through points, and laser weld or the beam weld is specified using the line. So these are the locations and these are the parts. So currently we are going to operate on the mid surface of this mesh. Now we are going to set up a rule for the generating a mesh. So for that we are going into the generating a rule. So we are going into the automated FEM and we are creating a mesh rule. So here you can see that there are different types of rule: octri triangle, octri tetrahedron, sweep mesh, beam mesh. So currently we are choosing the surface quad mesh because we require a quad mesh. Now we are naming the particular rule so we can use this for the other assemblies or the other products in the future also. So when we name it, it will get saved into the 3D experience platform. Now you are specifying the mesh type, first order, second order, or the quad dominant, or the only quads, or the mixed type. Here we are specifying the mesh size. So 5 mm I'm maintaining, and meshing technique is a default one. Now here you can specify the growth ratio across the geometry. Now here we are specifying the which geometry we want to consider for the meshing. So angle between the faces you can give input as per your requirement. Then quality for the meshing. So angle tria, then the angle quad, wrap angle, Jacobian you can mention over here. Then maximum nodal deviation. What is the deviation from the geometry? So from free edges, I'm mentioning the zero point 0.2 mm. It can be deviate. I'm allowing 0.2, and from the geometry also 0.2. Now I want to consider a hole above the 10 mm. So I am removing the hole from the 0 to 10 mm and specifying this particular rule, and putting a rule for the placing the washer from 10 mm to 100 mm hole with the minimum number of edges are 8 and the layer will be 1. So one layer washer will be placed around the hole and that layer height will be maintained around 5 mm. So 5 mm is the maintained height for that particular washer. So this rule is created. We have specified a particular parameter. I have applied it and click on OK. So this mesh rule is created as a document inside the 3 experience platform, and it can be referred for the future work for the meshing. So now I am clicking OK. I am OK with this setting. Now it will get saved into the 3D experience platform. Now we'll move towards to generate or applying this mesh rule to all other components. So I'm going into the automated FEM. Here I'm going with the advanced option, and I'm here selecting the procedure. So I want to generate a surface quad mesh here. So my procedure will be a surface quad mesh. In your case, it can be tetrahedral, hexahedral, and anything. Then here applied on which part? All parts I want to apply it on the main body. Then supports mean on which particular geometry I want to select. I will select it from the publication. So publication is the representation of that particular geometry. So it will automatically select the publication. Then I need to specify the which meshing rule needs to be followed. So I am typing the created meshing or specified meshing rule, that is the cradle mesh. I am just search it over search part, and I am selecting that particular cradle mesh rule. So this is the document where we have specified the rule. Now I have selected that specific rule for the meshing. Now once it gets selected, I'm clicking or going into the option. In this option, we can do a define a post processing task. Means after the meshing, what you want to do. So naming preferences will be there, quality criteria you want to execute, or the export options will be there. So it as per your requirement, you can set. Now I'm clicking on the OK to generate a mesh. So once you click, it shows you how many parts will be going under the meshing. Then once you click on run, it will open one window in which the some parts who does not comply with the meshing, we need to remove that. So these are the geometries containing lines and spot weld locations. So I have removed that and run the mesh specification or the rule based meshing. So now here you can see the progress of the FEM generation. So out of 10, how many FEM get generated? So here the process is going on. So you can monitor the process. You can keep monitoring it. So one FEM is generation is completed. So likewise, second, third, so you can monitor the process. You can refresh it, or if you want to interrupt it. Well, meanwhile, if you have put a wrong input into the machine room, you want to correct it, so you can interrupt it. That so you can see the now it is goes up to the four number of parts has been completed now. So sometimes it goes back, so maintaining that particular meshing rule with respect to the geometry. So sometimes it goes back to the another part 10 or the part 7. Now the mesh is generated. So some clarification needs to be done. So this is the automatic process. So I have said yes. So here you can see the report. Here you can see the all the parts are meshed and it is got notified. So here you can see the generated mesh. So here you can see the automated generated mesh. So this is the quad mesh and the triage is also there. And now we are going to hide the geometry to see the what is the status of the washer placement. So here you can see the washer placement is there, and it is accurately captured the features also, fillets also. So washer placement is all over the geometry as per the specified dimensions. So 5 mm height we have provided, then flow is maintained. You can correct this flow in a manual edit also. We are going to see in a next slide. So this is the mesh generated through the automation process. So rule-based meshing process. So all it is. Now we are moving towards the next point, that is a rule-based connection technique. So similarly, as you have seen in a meshing, so similarly you can create a rule for the spot weld connection creation, line weld, or the or the virtual bolt creation or the laser weld creation. So you need to specify the location with respect to line or the point. So here you can see the some templates for the line fastener. So line fasteners take care for the laser weld correction. In that we are going to place a shell element between the connection. We are going to maintain with the 3 mm size. We are going to apply a steel as a material to that particular weld element, and other specification you can mention. So similarly, we have the template or the connection rule for the virtual board where the bolting connection you want to define. So here you can see the head diameter should be a 30 mm, nut diameter should be a 30 mm. You can specify your particular diameter. Then nominal diameter, shank diameter will be a 20 mm need to be maintained. Then bolt will be a rigid type. Currently I'm setting as a rigid type. You can specify a deformable one. For that deformable, you need to specify a strain data or the material data over here. And you can also allow a preload. You can apply a preload by mentioning a preloading condition into the analysis. So that facility is available. So these are the two templates for the connection, for the first for the weld connection, second for the bolt connection. So now we are going to see the demonstration for the particular uh, connection template. So now we are similarly generating a template for a line fastener. Line fastener means a laser weld location or the laser weld connection. So here I'm going to call a already generated rule that is named as LFR. So we are going to see what we have defined in this particular rule. So in this rule, we have defined the material should be a steel, which should be a 3 mm. Then the connecting element should be a shell type element and a different parameters. Similarly, we can create a rule for the virtual bolt. So here I am going to select a virtual bolt. So here I am also importing a already created virtual bolt rule. So we are going to see what we have defined in that particular rule. So VBR is the naming correction. So these are the already created rules. So we can use the already created rule for the existing assembly also. So these rules are not restricted with the any assembly or the part. So here we have defined a head diameter 30 mm, nut diameter 30 mm, nominal diameter 20 mm, then the rigid type of connection. So if you have defined a deformable one, you need to provide a strain data. Now we are going to set up or applying this particular rule to the particular connection process. So here we are defined, previously we have gone into the mesh, now we are going into the connection. So here we are defining a particularly laser connection. So here I have selected geometrical line detection and mesh support as it should be applied on. Then placement should be a selection. So I will select all of the lines where laser weld or the line particular connection needs to be defined. So I will select these lines from the T tree of this particular assembly where the lines we have defined. So I'm selecting this particular line elements. So here you can see the laser weld front, left, right brackets. Here you can see it got the highlighted in the assembly. Okay. So once you selected the line, it's got highlighted where the line mesh get generated or the particular meshing element get generated or the connection get generated. Now I'm selecting the template for that particular connection. So here I'm using the LFR1. We have seen the what are the settings we have kept or mentioned in that particular rule. Now we have selected the template also. Now similarly, we are creating a procedure for the virtual bolt. So here virtual bolt detection, we are applying on the mesh support. So mesh is already done. We are applying on that. Then geometry will be the all consider geometry. Then here we need to specify search particular search criteria. So if you remember, we have specified remove 0 to 10 rods hole. So here I'm specifying hole above the 10 So here I'm specifying 25 15 to 25 as a diameter for the search. So between holes that are between 15 to 25 will be a consider for the connection purpose, bolting connection. So here you can see the length will be the 50 to 100 If you reduce it in that particular case, it will create a short bolt. Okay. Then the maximum angle between the axis is the 2 degree. Now I'm selecting a particular virtual bolt rule here. So we have seen the what we have specified 30 head diameter. Then the nominal diameter will be 20 that we are setting, we are importing. So we have also assigned a settings or the rule for the bolting connection. Now again we are creating a rule for the spot weld. Previously we have created a rule or the procedure for the laser weld. Now we are creating a particular procedure for the point. So here spot weld, we have selected the geometrical point detection. So here selection will be the point. In a previous section, we have selected the lines, but now we are going to select the points over here. So in the selection points will be required and search tolerance will be the 5 Now I'm selecting the points. So spot weld point, the specific collector I have selected. Now you can see that points got highlighted. So similarly, we are going to assign a template for the spot weld creation. So PFR is the name. Point fastener rule, we can say that. So point fastener rule will be assigned for the spot weld. So according to that rule, the point fastener will be created. So now all the rules and definition and all set. I'm clicking on the OK. So similar way, you can see the window. So now I'm ignoring that particular line and point product. So we are not applying any connection on that particular part. So I'm removing that from the particularly automated connection process. Now I'm clicked on the run, and similarly it will generate a particular process or the progress bar for the bolt. Now we are going to view how the connection have created. So here you can see the spot weld or the laser weld created through a shell element. So here you can see the shell element. So this also got a shell element connection. So this is the laser weld connection, so automatically got created. Here in this particular region you can also see the quad elements on the line. So specific region is followed, the line is followed for to generate a shell element. So I'm hiding the geometry, whole geometry, so we can see the total connection. So here you can see the bolting connections also. So we have given a length of 50 to 100 mm. If we specified some shorter length, you can also shorter. So here the shell elements. Then we have generated the spot weld element with the 1D element. So here 1D element is created. I'm selecting 1D element, so it will get highlighted. So this one are the 1D elements for the spot weld. Here you can see the bolting location. So above the 50 mm length, it got created. If we have mentioned the 25 mm length, so it will be a two bolting location. So you can also cover the intermediate hole also. So this type of connection you can automate. So all types of bolting, then the spot weld, then the laser weld or the bead, you can specify or you can automate this process by using this. Now you are handling a huge assembly, and now you want to manage this connection and the mesh. You want to edit particularly a particular part mesh. So how you go into that particular part? So for that we have a mesh and connection manager for the management. So in a mesh part manager, so you will get the access for the part for which the mesh is generated. So here you can see the mesh is generated for the all of the parts. So here type of mesh, then what is the size of mesh, then the color of mesh for or the color of that particular product representation. So here you can right click on this and you can edit the mesh also. What are the rules applied, you can see that in a manager. Then on the right side you can see the connection manager over here. So similarly it works similarly as a mesh manager. You can view the connections, line fastener, point fastener. So virtual bolt, line fastener means a laser weld connection with the help of the shell element or the quad element. Point fastener means the spot weld using the 1D element, and the virtual bolt is the bolting connection that we have seen. So you can click over any of the connection and you can edit it. We are going to see the demonstration also for that. So this is the particularly connected assembly. Now I'm going into the connection manager. So here you can see the list of the connection we have defined in this particular assembly. Now I'm clicked on the line fastener one. I'm going to editing that. So you will get the option. You can see the what are the supports you have selected for this particular connections. Then the what is the rule you have applied, what is the width of the particular connection, and what is the material. If you want to change the material for this particular location, you can change that in by defining manually over here. Then different options. So like this you can manage your line fastener. Similarly, if you go into the connection manager and here if you go into the bolt, you see the similar editing options. So the bolt head support is there, nut support is there, and diameters we have mentioned. Similarly, we are going into the mesh manager. Here you get the editation or management option for the meshing or the created mesh. Here you can see the at the bottom, here you can see the total number of nodes, total number of element, how many components have mesh, then the type of mesh. Here I'm editing it. Click on edit. So here which rule we have used, what is the size, what is the offset we have used, that all mention, and you can uh, change that according to you. you. And if you want to apply some colors to the mesh, you can change that by clicking on the color option. You can select the particular color and apply to the particular mesh also. So like this, you can manage your mesh connection for the larger assembly in a single window. Then managing the meshes by using the assembly of mesh. So assembly of mesh is a similar concept to the CAD part. So if you are aware about the CAD, so we have created some 3-4 parts for the assembly, and we link into by using that part we create an assembly. In a similar way, we create a mesh for the individual part, and we are going to connect that mesh with the assembly mesh. So means of the assembly of mesh we are going to create. So what is the benefit of the assembly of mesh? So particularly mesh created for the part, it get linked with that particular part. Suppose that part you are going to use within a different product line with the same dimension, you can use that part as a CAD as well as the FEM also. So FEM is stick with that particular geometry. It is not going to live at any step. So in other product line, you can directly have a mesh part also for the simulation readily available for the simulation or the reference purpose. So this is the benefits of the assembly of mesh. So we are going to see one example for this, how to do assembly of mesh, or how it is get reflected, and how easy to have a assembly to do a meshing. So this is the particular example in case of drone. Here we have created a mesh for the separate components. So this is the mesh for the arm, then for the base component, for the motor, color of the motor, rotor blades, and the stand. So different meshes we have created. Now we are going to assemble these meshes into the assembly. Now I'm going into the particularly into the mesh option and the contributing finite element. So in this particular window, you can see we can link the particular mesh with the particular part. So it will get reflected into the assembly. Once you are do the linking, in the background, your assembly start get creating. So here I'm selecting a particular FEM that I want to link with this particular part. So you can see the available candidates over here for the FEM. So I am selecting it. Now there are four representation or instances of ARM. So for that I am selecting reflect over all over the four instances. So here you can select in a one click, it will get reflected all over the instances where this part is used in the assembly. So similarly, you can create a assembly of mesh. Now in the background, it is creating a assembly or a mesh. Assembly of mesh is in progress while we have selected a particular FEM for the particular part. So now the linking process is completed. Now I will click on OK. Now you can see the assembly of mesh is also ready. Here you don't need to do a reflection, rotation, then the position of the mesh when you create a mesh for the single arm. In a traditional process, you need to rotate it, position it. That is not required because this particular role is CAD connected. So it will identify the CAD where it is the use, and it get reflected all over that particular location. Then we are going to also see one more benefit, the CAD, why CAD associativity is helpful while doing the iterations of the product. So here you can see the arm design. So now I want to change this arm design with a, I want to do some modification. I want to remove this triangle extrusions or the triangle pattern with the slot pattern. Now I'm editing this CAD. So I'm removing this particular triangle pattern, and I'm going to place a slot pattern instead of the triangle pattern. So I'm changing the geometry. Now imagine when you change a geometry, you need to do a remeshing. And again, when you do the remeshing, you need to again translate and rotate it at the other location. So now I have changed the geometry with the slot uh, design. Now I want to maintain this design and I wanted to check the effect of this design. Now I'm going into the FEM or the mesh. Now you can see the older mesh over here. That is a triangle mesh or the in a triangle pattern. Now I'm updating the mesh so it will accommodate as per the geometry edition. Now you can see it is got updated as per the geometry edit. Now my mesh is also aligned with the CAD. Now I'm going back into the assembly. Now you can see the changes at all 4 locations. So when you use this option or the role connectivity with the CAD, so it will be the helpful to reduce a rework over the meshing, assembling it. So it is going to reduce your modeling time or the model preparation time when you use the SBE role. Now, when you use this SBE role, it can be it should be useful with the different solver also. So it should not be restricted to only one solver. So it can be used. You can see the different files can be exported from the SBE role. So here I have mentioned some format, that is the .inp, .key, .bdf, .nas, and .fem. So these all format can be exported from the SBE role and can be used for the solving in the other solvers. So that .inp, it is related to the abacus. So you can export this particularly build model, you can import it into the abacus, and you can define your step and analysis procedure over that build model, and you can run that particular simulation. Similarly, you can export a LSDyna keyword file. You can import it into the LSDyna. You can define a boundary condition, loading condition, and the context in that, and you can run it to the LSDyna. Similarly, you can do with the BDF and the NAS, that are the Nastran extension. You can also export into the Nastran. Also, .fem and .bdf can be used for the optimization purpose in the OptiStruct. So .fem can be used into the OptiStruct directly. So you can export this particular build model and you can use for the further defining a boundary condition with respect to other solver. So this particularly SBE role, it is not restricted to the solver. It is the overall simulation model build engineer role. So it gives the access to the automate your process. You can use any of the solver. You can have a output in that format. Okay, so it will give you benefits. So these are the benefits when you use the simulation model build engineer. So you get the associative with the different CAD tools. Then you can build a finite element models efficiently using the meshing rules. We have seen that. Then the managing the sub-assembly connections, then generating a weld connection. We have already seen that. Then reusing the design data. So you can reuse the generated mesh over other uh, product line. Then you can manage the sub assemblies and utilize the automated assembly connector modeling. Then again, you can use the abstraction option. So in the abstraction option, you can remove unnecessary fillets, you can generate a mid surfaces, or you can remove logos on your geometry. Then if you want to add some surfaces, if you are importing a third party or the neutral file, you can work on that. You can add the surfaces. So some basic surfacing tools are provided, geometric cleanups tools are provided in the abstraction tool in the SBE role. Then you can collaboratively model management for building and sharing the model, particularly suited for the large assembly. So if you are working with a single part, you are generated a mesh and it can be used in a 3-4 product line. You can use the same FEM in a 3-4 product line. Again, one more benefit it has, you can generate a different size of FEM. Suppose you are using a 2 mm mesh size for the detail analysis and a 10 mm mesh for the large assembly analysis. You can maintain a single size or the different size of meshes with the single part also. So that benefit you get with the SBE role model preparation when you use. Okay, now we have completed with the technical session. Now I'm handing over session to the Aniket, and we have the questions if you have any.
Okay, thank you, Kedar. Uh, Thank you, Kedar. We already do have couple of questions. So also I request our attendees, if they have any questions, they can type down the questions and I will speak out the questions and Kedar can answer those questions. Also, you can raise your hands. There is an option to raise your hand and I will unmute you and you can ask the questions. So, okay, Kedar, our first question is, which CAD tool can be connected to SVE role?
Okay, so CAD tool can be a CATIA, SolidWorks, Creo, Uginix can be connected to the specific SBE role. You can have a bidirectional associativity with these CAD tools.
Okay, thank you. So our next question is, can we get mesh details quality report?
Yes, you can get a detailed quality report, and you can see a bad quality element in a single window, and you can go and you can edit that particular element. Yeah.
Okay, our next question is the tool have control over the node and elements?
Next question. So yes, tool have a control over a node and element. You can delete the element, you can create the element itself, you can move the node for the adjusting the quality criteria, you can align the node, you can split the element, you can merge the element, you can divide the element. So all of the controls over the node and the elements are available with this SBE role or the simulation model build engineer role.
Okay, so we have one more question. Will the SBE role come under the same license of Abacus or separate license?
So this one is the separate license. It is just a pre-processor load. So here you can define the pre-process your models. So model building role only. Yes, this is the separate one.
Okay, thank you, Kedar. I think we don't have any more questions with us, but definitely if our audience have any questions, they can definitely connect with us. Our details would be shared on the screen. Okay, so I would like to thank Kedar for delivering a very insightful webinar today, and I'm very confident it was very helpful for our audience today. I would also like to thank our audience for taking their time out and joining this session. If you have any queries related to the subject matter or any requirement, you can always connect with us. You can reach out to us at any time and we would be happy to address your queries. So after the webinar, you will receive a link to share your feedbacks and inputs or share your queries. We request our audience to please fill the details and we will get back to you with all your queries. So please do keep an eye on our upcoming seminars and webinars. You can follow us on our social media platform. Thank you.